So my name is Devis Tomasso. I'm from, hopefully you don't see this bar. So I'm from Queen Mary University. I've been working in Queen Mary for the last 4 or 5 years. And I just want to, before I start giving a bit more detail about the things I will present today, just to give an overview of what we do in my group, just in case there are people that would like to contact me regarding possible collaborations and just discussions. So I'm mainly interested in crystalline growth and nucleation phenomena. So I work on both trying to understand what are the early stages of growth and nucleation for inorganic materials. For example, here is an example of how we managed to determine what are the early stages in the formation of hydroxyapatite, as well as try to develop methods to determine, again, the early nucleation stages of organic materials. So in this couple of applications, we develop a method and then apply it to try to determine what were the species that were present in solution in the case of caffeine. So I'm also interested in processes occurring in electrolyte solutions, and in particular in trying to link aqueous thermodynamics with molecular processes that can be simulated using techniques such as molecular dynamics. And one thing that I've also been doing, probably a bit less, is try to simulate amorphous and nanoporous materials, things such as water confinement in nanospaces, such as hydroxyapatite or glasses. Okay. So, but today I wouldn't like to talk about what I've been doing so far. I just want to talk about what I've been doing the last 6 months and what I'm going to do in the next 2-3 years. And in particular about the FunMin project. So the FunMin project is a project funded by the European Union, where Queen Mary is the leading university, and is in collaboration with other 4 universities in Europe: Granada, Oviedo, Grenoble, and Utrecht, together with a company, Cambridge Carbon Capture, that is based in Cambridge. So the consortium is called FunMin, and it stands for Fundamental Studies of Mineral Carbonation with Application to CO2 Utilization. So just to give you the context of the project, so you are well aware that one of the major issues that society has to face today is the high levels of carbon dioxide. And one of the challenges, but also opportunities, is try to transform CO2 into some sort of added value products. So this is a statement that I took in from a report from BASE. It says that CCUS stands for carbon capture and utilization and storage, can create new industries and markets through the use of carbon dioxide. So a lot of work has been going on in trying to reduce CO2 into chemicals, but what we are interested in mostly is try to transform CO2 in building materials. So in this figure here, you've got this is a colleague of mine, Michael Evans, is the CEO of the company Cambridge Carbon Capture, and they've developed a technology called CO2LC that manages to transform CO2 in a mineral, in particular magnesium carbonate. So the process itself is quite easy, and it is shown here in this figure. So you've got CO2 that, well, there's plenty of CO2, and actually it's quite easy to dissolve CO2 and then to form your carbonate in aqueous solvation, in aqueous solution. Then you've got your magnesium sources that also are incredibly abundant, okay? Things like magnesium silicates, for example, that could, in theory, sequestrate all CO2 that is emitted by all fossil fuels available in nature. So it's also, that's very viable, and it's possible, relatively easy to go from this magnesium source into magnesium ions. But then the formation of magnesium carbonate, that could be a solution to try to transform CO2 into an added value mineral, is a very slow process, okay? So one of the major difficulties that companies such as Cambridge Carbon Capture have is try to increase the rate of formation of magnesium carbonate, this particular step here, okay? So just to give you also, the FunMin consortium is a consortium that between universities and in particular groups with different expertise. So we have got theory, London, so we are leading the theory part of the project. So Utrecht is an expert in geochemistry, Grenoble in spectroscopy, and Oviedo and Granada in the characterization of minerals. And what we would like to try to do is try to guide industrial technologies that to permanently mineralize CO2 into minerals, and in particular into magnesium carbonates. Okay, so just to give you an idea of what is of the process of mineral carbonation. So you have got your ion solutions. For example, you have got your magnesium in solution, and the first step that needs to occur is that you need to have a dehydration process or a partial dehydration process. It means that you need one or several of the water molecules that are coordinated to the magnesium needs to go outside of the first hydration shell, and in a way that the carbonates in solution can form your units of magnesium carbonate, and then you can have the formation of your clusters of magnesium carbonates, and then you got the process of growth. Okay, and that hopefully then you can, by doing this, you can hopefully start from a solution that contains magnesium ions and carbonate into a mineral that can permanently sequestrate CO2. The long-standing problem in these processes, and in particular two processes that are related with the formation of magnesium carbonate, is that magnesium water, but the magnesium water interaction is very, very strong. So the difficulty in precipitating magnesite, magnesium carbonate, has not been ascribed with the slow kinetics of magnesium dehydration. So with the following step here. So with the removal of the water molecule from the first hydration shell and subsequent steps. This process of magnesium dehydration is going to be also important in other steps such as nucleation and growth. So there is some evidence of this. So this is a paper that we published a few years ago. And so these are inelastic neutron scattering experiments of calcium carbonates, hydrated calcium carbonates, where my collaborators from Grenoble increasing. So what they've done, they increased the amount of magnesium in this mineral. And what they did, they use a technique called inelastic neutron scattering to probe a particular region of the water. And this region is a vibrational mode region, so it's a soft part of the vibrational spectrum. And what you can see here, you got a small but significant shift of the peak essentially, as you increase the content of magnesium, this peak shifts to the left. Okay. So what this means? So we tried to. So what we did, we did some calculations which are reported here, where we computed the vibrational density of states of the magnesium of the water molecules that are surrounded to the ion, and we actually saw that, and we compared the behavior of the water molecules around the calcium and the water molecule around the magnesium, and what you can see is that we show a shift of the peak associated with the vibrational modes towards right. So there is an increased rigidity for the water molecules that are coordinated to the magnesium. So that was a first indication that as you increase the content of magnesium in these minerals, the water molecules around the ions become more and more rigid. Okay, but this project is trying to get a further insight into these processes, and in particular in how we can accelerate the formation of magnesium carbonates from solution. So the project is about applying a combination of atomistic simulation and spectroscopic measurements to reveal what are the molecular processes that control the magnesium carbonate formation, the dehydration, the nucleation, and the growth. So in this scheme, I just report the range of techniques that we are going to apply during this project. Okay. So today, I want to just to tell what we have done in the last 6 months in terms of trying to characterize the process of magnesium dehydration by means of a series of, by applying a combination of computational chemistry techniques. So the simulation tools that we employed are summarized here. So we use GROMACS poly to conduct molecular dynamic simulations. So that's a very simplistic view of how molecular dynamics works. Then we use CP2K to do ab initio molecular dynamics and quantum espresso to we'll use quantum espresso to characterize solid state phases of magnesium carbonates. So molecular dynamics is a very good technique, but the issue of molecular dynamics is that you can only probe low energy states in your potential energy surface. So we also make use of non-sampling techniques by making use of the plumed code in order to probe high energy states in the magnesium dehydration process. So this is the work that Dimitrios, that my postdoc has been doing in the last 6 months. So the first thing we wanted to do is try to characterize the mechanism of magnesium dehydration. So what is the mechanism through which water molecules go in or out of the dehydration shell of magnesium? So that what is reported here is the free energy surface that has been computed using 2 collective variables or 2 reaction coordinates. One is the coordination number, and the other one is the distance between the magnesium and water. And to cut the story short, what this graph tells us is that in order to remove your water molecule from your first hydration shell, you have a dissociative mechanism. So you start with a 6 coordination environment, you go to an intermediate corresponding to a 5 coordination environment before going back to a 6 coordination environment. Okay,